In this video, we're going to cover section 2.1 on the logical forms and logical equivalence. So first, let's talk about what is a statement and what are connectives or connectors. So a proposition is a sentence that is going to be either true or false, but not both at the same time. So some examples of a statement will be 2 plus 2 equals 4, which is a true statement. Cincinnati is in Ohio, which is a statement that is true, and 2 is less than 1, which is a statement that is false. Sometimes you have things that depend on variables, for example, x bigger than 3. This is not a statement or a proposition per se, because it depends on the x value, and it might change value of true or false depending on who x is. If you make a question like is it raining, or a command like close the door, that's not a proposition. The proposition must have a very clear or at least imply a value of true or false. So once we have statements, we have three basic connectives to build compound statements. We have the negation or the not, we have the conjunction or the and we have the disjunction or the or. So first, with the negation, if we have a statement P, the negation is just going to mean not P. For example, if I say Carlos is tall, then the negation of that will be Carlos is not tall. Now, in conjunction, I'm usually getting two or more propositions together with the n. As an example, if I have a proposition P, Carlos is tall, and proposition Q, Laura is smart, then the conjunction will read Carlos is tall and Laura is smart. This disjunction functions in the same way with the or, and I will go with something like Carlos is tall or Laura is smart. The or is inclusive, and it's going to be true if at least one of those is true. If Carlos is tall or Laura is smart, any of those two is going to make the or statement true. Now, many English words translate to the same connective, but is equals to n. For example, we can say John is not wealthy, but is healthy, or but healthy. We can use neither or nor for not. For example, John is neither wealthy nor healthy. This will be a negation on each of the propositions. We can use sometimes however, although, yet, and they're often going to mean and as well. So pretty much many different ways to write in English some of these logical connectives. Now let's move to truth tables. So truth tables are ways to show the true value of a compound statement for many possible combinations. So for example, for the negation of P, we start with a proposition P. It turns out that proposition P can be true or can be false. So the negation, not P, is going to have the opposite truth values. If P is true, then not P is false. If P is false, then not P is true. In general, not P is going to have the opposite truth value of P. Now, for the conjunction and the disjunction, we need to make a couple of considerations. So first thing is that you're going to notice that the table is bigger. Usually the truth tables are 2 power to the number of propositions that we have. So here, because we have one proposition only, the size of the table is 2 to the 1, which is 2, so we have only 2 entries per column. Here, because we have 2 propositions, then it's 2 to the 2, and we're going to have 4 entries per column. Now, why that happens? It happens because if P is true, then Q can be either true or false. But in the same fashion, if F is false, then Q can be true or false as well. And so once that we have those statements, then we can see what is the combination of them. For example, for P and Q, this is only going to be true when both of them are true. Otherwise, it's just false. So if I have P is true and Q is true, then P and Q is true. Otherwise, it's going to be false because you're having one truth value and another false. So the combination of that's just going to make the proposition false overall. The opposite happens with the OR. With the OR is only going to be false when both of them are false. So only in the case when P and Q are both false, the OR is false. You can think of this as the conjunction is like having a half-truth. When you're saying something that is true, but then you say a lie, then the whole thing becomes a lie because just one piece of them is a lie. And the disjunction is the opposite. It's like you're getting to pick what's the best option for you. So let's say you're picking a coin and you have one coin that is real coin and another is a forgery. So if they give you to pick this one or this one, well, you logically will pick what is true. So essentially you're doing the same with the disjunction. You get a selection between something true and something false, you're always going to go and pick the truth unless you have no option and everything is false. Okay. Now, once again, as I was mentioning, for n variables, we have 2 n rows on table. So if we have something larger like a true table with 3 propositions, now it's going to be 2 to the 3, and it's going to be 8 pieces here. So here we have an example here of something that contains P, Q, and R. And so we have also P or Q, and we have negation of R. And the final statement that we want to check is P or Q and minus R. And that's just going to be a big A pieces table of true or false. So every time that we're building this type of table, we're just going to start by P, then go to Q, and then go to R. As you notice, we have 4 truths and 4 false. And then for this true, Q can be true or false. And then R can be true or false. So that's why we have so many options. Now let's go with the idea of logical equivalence. So 2 statements are going to be logically equivalent if they have identical true tables or identical true values for each possible combination. We're going to say that they're logically equivalent if something like P is equivalent to Q. We use this notation with the 3 bars. And to prove equivalence, we construct true tables. And if the final column of each statement match in their truth values, then they're equivalent. The easiest example of that is the double negation. Negation of the negation of P is just P. And you can check that that is true because if you take P, negate that, then the true or false value are going to change to false and true. But if I negate that again, then the values revert back. So notice that P and negation of P, they have the same truth values. And so because they have the same truth values, then the first and the last column match, and these are equivalent statements. Now, we're going to do more complicated examples of this on the examples videos. But for now, this is the basic idea. Now, there are quite a few important rules with this statement. One of the most important is the Morgan's Law. And so the Morgan's Law is telling us how to negate the and the or statements. So if we have the negation of P and Q, we're going to get negation of P or negation of Q. And if we have the negation of the negation of the or actually becomes an and. So negation of P or Q becomes negation of P and negation of Q. So to negate an and, we just need one of them to just not be okay. Or negation of P and Q means that not P or not Q. One of them is just enough. But to negate that one or the other things are happening, if I want to negate both of those, then I need to negate both of them at the same time. And that's why it becomes an and. So in general, the key pattern is to change and or to or and to negate each of the parts. So this is super important when you're doing Morgan's law. Now, we can prove this by logical equivalences. Notice here we're going to build by P, true and true, false and false. Then Q becomes true, false. P and Q, then we know that is false unless they're both true. And so we get this statement. Now we do the negation of this. And so it becomes false, true, true, true. And now we get to also do negation of P and negation of Q, which is just flipping the values of these ones here. And then we can build negation of P or negation of Q, which will take this values into account. So for example, false or false is going to be false, false or true, true, true or false, true, true or true, true. Now, notice that this column, negation of P and Q, has the same values that negation of P or negation of Q. So because these columns are identical, then this is an equivalent statement. Now, let's see an example of applying Morgan's law to something in words and in symbols. So we have the train is late or my watch is fast. Then I can think this as the proposition P, the train is late, and Q, watch is fast. So the original here would be in a statement of the form P or Q. The negation of this, it will be negation of P and negation of Q, which will mean in words, the train is not late and my watch is not fast. Now, to negate, another example to negate something in more mathematical terms, if I have x is less than 2 or x is bigger than 6, clearly this is P and this is Q. We have a statement of the form P or Q, and the negation will be not P and not Q. So negating that will be, well, x is bigger than or equal than 2, and x is less or equal than 6. Notice that the negation flips this symbol because this is less than 2. So if I negate that, it's going to be bigger or equal than 2. And so this combination will give me the interval is between 2 and 6. Now let's now that we define what is an equivalent statement, we can introduce the knowledge of tautologies and contradictions. So a tautology is a statement that is always going to be true, regardless of truth values that are in place. So for example, if I give a statement of the sort, it is raining or it's not raining. Well, this is like covering the 100% of possibilities that you have. It is raining or it's not. That just covered everything. So that's going to be a tautology because that's always going to be true, regardless. So if I think it's raining is P, it's not raining is going to be Q. It's going to be not P. And so if I do P or not P, I'm going to get something of the sort of true or false, which gives me true, and false or true, which still gives me true. So always is true for that statement, and this is a tautology. Now, the contradiction is the opposite. The contradiction is a statement that is always going to be false, regardless of the truth values. The symbol for that is going to be the contradiction, which is a C, usually. And we can kind of pick the same. We can do, it is raining and it's not raining. Well, that is a contradiction. Both things cannot be happening at the same time. So if you pick P at is raining, then it's not raining is negation of P. And if you do P and not P, you will get true and false, which is false, false and true, which is false. So always false, contradiction. Now, we have a bunch of important logical equivalences, and we're going to check some more of this in the examples. But there are here some of those particular laws. So we have the commutative laws, which is if you have P and Q, that's the same that having Q and P. Or if you have P or Q, is the same that having Q or P. That doesn't change anything. Associative laws, which is if you have P and Q and R, that's the same that's saying P and Q and R. So who goes first doesn't matter. if everything is an and. If it's an or, is the same thing. You have P or Q or R is the same that P or Q or R. Now distribution, you gotta put attention here, because here you have an and distributing over an or an or distributing over an and. And what's going to happen is that this is going to split this into an and situation for each of the propositions. So this becomes P and Q or P and R. And in this case, the or distribution, P or Q and P or R. Now, the identity loss as well. We have P and true is always just going to be P, and P or contradiction is always going to be P. So any of these two is going to give me my initial proposition. The negation loss will give me values of true or false. So for example, if I'm picking P or not P, that's always going to be true. Why? Because one of them is true, so I can just pick the one that is true, and that's it. And if I have P and not P, well, this is always a contradiction, so it's just going to lead to that. The double negation, we already saw that, and the Morgan's law as well. Now, in summary, we have the statements or propositions that are sentences that are true or false, but not both at the same time. We have connectors, the not, the and the or. And we have the P and Q, which is true when only both are true. The P or Q, that is false when both are false. Truth tables show all possible true value combinations, and logical equivalences are when we have that two propositions are matching their truth values. The Morgan laws are critical for negating compounded statement with and or, and they negate and switch the and with the or. Now, it's very important not to mistake confusing the and the or, and remembering that P and Q is only true when both of them are true, and that P or Q is true when at least one of them is true. You gotta be careful with negating the Morgan's laws incorrectly. So, for example, if you do negation of P and Q, you gotta be careful not to just distribute the negation in each of those cases, or just remember in general that you are not only negating the proposition, but changing the and for the or. Also, make sure not to believe that or is exclusive. In logic, P or Q is true even when both of them are true. Okay? All right, so this is the end of section 2.1. Now we'll move to checking some examples.